I want to tell you that all of you. Okay. Let's start today's session. Module 4 devoted to digital voltmeters, digital multimeters and wedges. So digital voltmeters are nothing but measuring instruments which will convert analog voltage signals into digital readout. So this thing you have to note down. It is simply converting analog voltage signal into digital readout, means some numerical values will be displayed. So your analog voltage signal voltage is converted simply into some numerical values. So that is the duty of digital voltmeters. So it doesn't mean that it is going to convert an analog to digital signal, but more precisely we can tell that it is converting your analog voltage signal into some readable digital numericals. So the types of digital voltmeters are actually based on the number of digits. So how many number of digits you want to display or you want to see on the display screen, that is going to decide what kind of digital voltmeter we want to design or we want to purchase. So actually it will tell the number of significant digits, significant figures, including both the decimal digits before and after that decimal point. So number of digits is nothing but the number of significant bits which are going to decide one of the factor to be considered when you are going to design or to purchase the digital voltmeters. Another one, the number of measurements. So whether you want to measure resistance, you want to measure voltage, maybe AC or DC, you want to measure current, again it is a AC or DC, or you want to measure some other parameters. So all these things are to be kept in mind when you are going to choose or to purchase or to design the digital voltmeters. So further factors are going to come under its performance, like the accuracy of the digital voltmeter, how much your reading is accurate. You are measuring by some means the voltage you are getting 50 volts, and if your DVM is not showing 50 volt, then it is having some error. So the accuracy, how much it will be, means tolerance plus or minus 5% or 10%, that you have to see there. Speed of reading, so how fast you are getting the reading. Types of digital outputs, means whether you want digital output, you want analog output, you want the output to be stored. So such kind of things, or digital outputs could be something like uh, whether you want to have LED or LCD based digital outputs. So all those different varieties of outputs are going to decide or kept as one of the parameter when you are going to select or to design these digital voltmeters. So by all these things, one thing what we can ensure is that digital voltmeter is simply an instrument which is helping us to see how much analog voltage is to be observed or measured. So the comparison, if you look at this one here, so this is another important factor in this module. So many times it has been asked, you should know the basic difference between the digital voltmeter and analog voltmeter. The first one, digital voltmeter, it can supports both AC and DC voltage display, whereas analog voltmeter can measure only up to the AC voltages. It is not going to support digital voltage readings. Coming to another one, second one, in digital voltmeter, because of a numerical readout, it reduces human error, means gross error can be reduced, parallax error can be reduced. So that is because of our difference in position, that we are standing before the instrument, and with respect to the position of the our vision, we are getting a small amount of error reading the numerical readouts or measurements from these instruments, resulting into the parallax error. So by reducing the gross and parallax errors, it will enhance the reading speed in case of digital voltmeter. So whereas an analog voltmeter does not reduce any gross or parallax error, but can be avoided with care. You have to take care manually. Therefore, little support in increasing the reading speed as compared to the digital voltmeter. So digital voltmeter, digital readout is there. You can stand anywhere like anything. You can get the same numerical readout, but that is not the case with analog voltmeter. So the third difference will be the output in digital form useful in further processing and recording, because it will provide us a facility to store the whatever the output we got. But that is not possible in case of analog voltmeter. You cannot store the analog readings there. For that, again, it should be converted to digital again. So that's why the output is not suitable for the further analysis here, because a lot of difficulties are there to store it. Again, if it is possible, we have to process it for the further analysis. The fourth one, in case of digital voltmeter, so because of the digital circuits which we are using in order to design the digital voltmeters, circuitry parts, so we can see that most of us or even student community feel more comfortable with the design of digital circuits compared to analog circuits, because there you deal with only two states there, either 0 or 5 volts or maybe one state, no any intermediate states. Even it is very simple to design any combinational sequential circuits as compared to analog circuits, because in analog circuits you have to consider a lot of factors in order to design one analog circuit. That is not the case in digital circuit design. And moreover, digital circuit can deal with only with respect to the truth table, which is just based on the 0 and 1, two states, binary states. But whereas in analog circuits, your input itself is going to change very instantaneously with respect to time. From 0 to any value, even less than or more than 1. So because of these reasons, the design of digital parts of this digital voltmeter will become very much simple and not complex as in case of digital voltmeter design. So hence, it will become more portability, size can be reduced. So whenever the system will become more portable and compact, power consumption will be reduced and cost will be drastically reduced. So those things are not there in case of analog voltmeters because of these reasons. So like that, guys, you need to explain the trade-off between the digital and analog voltmeters here. So far, what we have learned, how to define the digital voltmeter, what parameters to be considered when you are going to set the digital voltmeter, or how to choose the digital voltmeter, or what parameters to be kept in mind when you are going to design the digital voltmeter. So another thing what you have learned is the basic differences between the digital and analog voltmeters. So one thing, you never use the table whenever you will get the question to discuss the trade-off or comparison kind of questions. So some of the important performance parameters here. Input voltage range may be from plus 1 volts to plus 1000 volts with automatic range selection. So here you can see, so I have shown here plus 1.000 volts. It will indicate that how many significant figures we are using. Means how many number of digits I want to have on the display screen. So here totally 4 digits are there, including decimal digit means it is going to be 5. So this is indicating that input range means it is indicating two things here as far as the DVM performance characteristics are concerned. One thing, it is indicating the numerical voltage range ability of your DVM. Means it is able to measure from 1 volt to 1000 volts. That to plus only, no any minus voltage. And another thing is that how many significant figures or numerical can be displayed on the screen. So these two things are we can predict from this first outstanding quality of the DVM. The second one, absolute accuracy, here he has quoted as plus or minus 0.005 percentage of the reading. Plus or minus 0.005 percentage. So the third one, resolution, which is a part of in a million, that is going to be 1 microvolt read on 1 volt range. So that is how, what is the smallest voltage reading you can measure, you can read from the DVM. So that is specified here in terms of the resolution. Fourth one, the calibration, that is internally done for to stabilize the reference sources. That is going to be independent of the measuring circuit. Means that what do you mean by independent of circuit to be measured? Means before you are going to before you are going to make use of this DVM as a part of the circuit. Hello? Yes. So independent of measuring circuit means calibration of the DVM should be done before it will be used in the circuit for the measurement purpose. ಅಂದ್ರೆ ನೀವು ಸರ್ಕ್ಯೂಟ್ ಒಳಗೆ ಅದನ್ನ ಮೆಜರ್ಮೆಂಟ್ ಪರ್ಪಸ್ ಕನೆಕ್ಟ್ ಮಾಡೋಕ್ಕಿಂತ ಮುಂಚೆನೇ ಅದನ್ನ ಕ್ಯಾಲಿಬ್ರೇಟ್ ಮಾಡಿರಬೇಕು. So but what do you mean by calibration? I already discussed that one in the error or measurement part. So the pointer, suppose if you are using analog, it should be exactly on the zero. Or if you are using the digital voltmeter, now we are using digital voltmeter, without connecting it to the circuit, what reading it is showing, it should show the zero only. Even not negative number, it should not show. You have to make it zero exactly. That is called calibration without connecting into the circuit. Otherwise, by that much amount of reading, you will be either advanced or delayed, introducing into the some kind of error in the measurement. So the fifth one is output in the BCD form or for printouts or digital processing. You should be decided in advance. So whether you want the output suitable for the printouts or you want it to be stored and used for further digital processing or you want some decimal form of digital output. So these are some performance qualities of DVM which are normally available. We have taken some typical characters here which are commonly available or used for the DVM. So next we can study RAM type digital voltmeter. So this is, guys, you listen here carefully, a very important, the first type of digital voltmeter we are going to study in the module 4. As you can see here, the name itself it will indicate RAM type digital voltmeter. Means we are using RAM signal. RAM signal means what? We know the sinusoidal signal. It is having both positive and negative peaks and its amplitude is varying instantaneously. We have the square wave pulse here, clock pulses I have shown here, you can see here, it is like this. Ramp is like this. Sawtooth waveform you have seen, so it is similar to that one, that is a ramp. Here you can see, we are considering one ramp signal that is decreasing from plus 12 volt to minus 12 volt. Means we are considering one negative going ramp having the negative slope, you can see here. So we are using such kind of a negative going ramp as a reference, or you can say the main key reference in order to measure the DC voltage. What is the measured DC voltage to be measured here? You can see here in the figure, it has been shown with the dotted line, voltage to be measured. So this is the DC voltage that is fixed in amplitude, having zero frequency, and we have to measure this DC voltage, the dotted line, using this ramp, negative going ramp, that is decreasing from plus 12 to minus 12. So this is the basic concept. So what is the basic concept here? DC voltage represented by the dotted line. How much it is there from 0 to above the positive y-axis, we don't know. We have to measure that. For that, I am using a negative going ramp, which is decreasing from plus 12 to minus 12. So let us see what is the basic concept here. I will identify 2 points here. First one, denoted by first coincidence. So negative going ramp is decreasing, start decreasing from plus 12 volt. It goes on decreasing, then here. Here we will get one come across, it will first time cross the DC voltage to be measured. Means ramp when it is decreasing from plus 12 volt onwards, where it is first time going to cross voltage to be measured, DC voltage to be measured, that is a dotted line. We call it as a first constant. Then it doesn't go on decreasing, ramp, again it is decreasing. Then you can see where it is going to cross the 0. We call it as second coincidence. Between these two, I am going to send some clock signals or clock pulses to be measured. So these clock pulses I have to count and display it in the form of some display. That is equivalent to the DC voltage to be measured. This is the main basic concept. Okay, what I will do, what is the main basic concept, I will have to listen here carefully. I have the counter here which is going to generate the clock pulses of some specified width. I will start counting these pulses from the first coincident to the second coincidence. Whatever the clock pulses are counted during this duration, first to second coincidence, will be counted and displayed. That is equivalent to the DC voltage to be measured. That's it. So two main basic concepts are there. The first step, I have to identify the first coincidence where ramp is going to cut your DC voltage to be measured. And at that instant, I will start the counter. I will start the clock pulses and start the counters to start counting these clock pulses. And I will identify the second coincidence where my ramp voltage will cross the 0. I will compare that one, where it is going to cross, it will become equal to the 0. And at that instant, I will stop counting the pulses. So whatever the pulses are counted will be logged, sent to the counting display to be displayed. That is equivalent to the DC voltage to be measured. So this is the basic concept or operating principle of the ramp type digital voltmeter. So let's try to understand this one with the help of a simple block diagram. So operation is very simple. So first one you can see what you have to do here. Initialization. It has got totally 3 parts here. Initialization part, input comparator and output comparator. First you have to draw this block diagram. So figure shows a typical block diagram of ramp type DVM. It has got some of the important blocks. I will go on explaining these blocks. You can listen here carefully. Along with these 3 main parts here, initialization. So first part you can see the test DC input that is to be measured is applied as input to the ranging and attenuator. Ranging means it is a part of this block circuitry that is allowing the user to select what particular range we want to use to measure the voltage. Whether you want to select the range 0 to 5 volt, or you want to select the range from 0 to 10 volt, or you want to select the range from 0 to 100 volt, like that. Next one is the attenuator. Attenuator, it will help us. Suppose if the DC input voltage you want to measure is very large or very small, that you cannot see it comfortably on the display of a CRO screen, oscilloscope. Then in that case you need to attenuate it proportionally. So if the input DC voltage to be measured carries a very large voltage, In that case, we have to reduce it proportionally with the help of alternator. Only in that case. Otherwise, no automation is required. It is optional. Okay. So, but before using all these things, your this parameter should be calibrated, should be kept at exactly 0. That is called initialization. So next one, the output of this DC will be coming as it is, will be applied as one of the input to the input comparator. See guys, here we got two important comparators here. One is the input comparator that is going to check this first coincidence. Means where the first time the ramp is going to cross your DC voltage to be measured. That is detected by the input comparator. 0, when ramp is going to cross the 0 is detected by the ground comparator or the 0 detector. It is also known as 0 comparator, 0 detector. You can see here it is one of the input is 0 and ramp generator is there. Sample rate multivibrator, it is going to generate the ramp signal of a specified slope with help of ramp generator. That is applied as one of the input to the ground comparator. Means the ramp signal is coming here and is also applied to the input comparator and ground comparator both. In the input comparator, the negatively going ramp is always compared with the DC input voltage. One of the input you can see DC input is there. In input comparator, you can see here, listen. One of the input we are getting here, it is a DC. And another input, second input we are getting it as a negatively decreasing ramp. Means input comparator, what it is doing, it is continuously comparing the negatively decreasing ramp with the DC input voltage. And where the first time the negative decreasing ramp will cross the DC input, it will activate its output. That will become 1. That is, we call it as a start pulse. When start pulse is applied to the gate, when start pulse it is called because we can see here the count oscillator here I have shown here. It is continuously generating the small clock pulses. If circuit ಯಾವಾಗ ಆನ್ ಮಾಡಿರ್ತೀರ ಅವಾಗ clock pulse oscillator generate ಮಾಡ್ಕೋತಾ ಇರ್ತದೆ. But these clock pulses will be applied to the counter only when we will get the input comparator output 1. So by getting the input comparator 1 means when negative going ramp will cross the DC input voltage to be measured first time, this input comparator would generate the 1, that is the start pulse, will tell gate is opened and the oscillator clock pulses will be applied to the counter to be counted. The clock pulse open adu and applied to the counter when during first coincidence. How long these clock pulses will be applied to the counter to be counted? Until we get the stop pulse. When we will get the stop pulse, with the help of ground comparator, which is continuously comparing this ground 0 with the negative going ramp. So when the negative going ramp will cross the 0, its output will become, you can see AND gate, it is 1. When both will become high, we will get the 1. When both will become high, when negative going ramp and 0 will both will equal, we will get the stop pulse. Then it will stop these oscillator already generated the clock pulses to be applied to the counter. So counter will be now latched from this circuit. Latched under counter illitana connect agittu. Now after getting the stop pulse, it will be temporarily disconnected. Latching means what? Kondiyakodu ashte. Latching means kondiyakodu. Temporarily disconnected. Why? We want now the counter to count all the pulses from start to stop pulse. Then after that, it will be connected to the readout display. Until that, it will be latched. Counter will be latched from the readout display. So this is how your ramp type digital voltmeter is going to work out. So let us see the advantages. Ramp type circuit is very easy to design with the low cost circuit components. Only a very simple R and C type of elements can be used, which are very low cost and easy to design. Output pulse is transmitted over long lines. We can transmit the output long distance. Disadvantages: the performance or accuracy of this RAM type DVM depends on how accurate you are going to generate this RAM signal. The slope of this RAM signal should be very much accurate. That is going to decide the accuracy of our DVM, RAM type DVM. Okay, that is one limitation. That's why he has told single RAM needs excellent Cat6 of RAM and time measurements. Second one, large errors are possible when noise is superimposed on the input signal. So whenever we are going to measure the RAM voltage using RAM type DVM, if you get any noise interference along with the measurement in terms of during circuit, some short noise or some thermal noise will get, or somebody will talk, some man-made noise will get, that is superimposed or mixed up with our measured voltage. That should be minimized. But that is not possible in case of ramp type DM because you got only one negative going ramp is there. Okay. Only with one negative going ramp, we cannot have any means to minimize this noise. Somehow you have to minimize that. For that, we need another positive going ramp so that whatever the noise we got during negative going ramp, that can be the positive going ramp can be used to minimize that noise we got during negative going ramp. So means we want to adopt here some averaging or integration technique here to minimize the or average out the noise throughout the signal. So normally we learned that integration or averaging is going to minimize the value. It is going to reduce the value. If I will ask you to take the average of 1 to 10 numbers, you obviously will get a very low value. So in the same manner, we are going to average out the noise here by using negative and positive going ramps. Negative going slope ramp and positive going slope ramp. That's why it is known as a dual slope integration type voltmeter. Next one we are getting, that is going to average out the noise we got in the negative and positive going ramp using integration. So whatever you can see here, this is the operating principle I am telling here. Listen here carefully. So this one is the graph which is going to explain you the operating principle of a dual slope integration type DVM, or also known as voltage to time conversion type DVM. Here we are using two slopes because of the drawback of the ramp type DVM. Because what is the drawback in ramp type DVM? We got to use there only one negative going ramp there, no any positive going ramp. Negative going ramp again noise adagiತ್ತು. We haven't got another chance to minimize that during positive going ramp. So that's why we are clubbing positive going ramp along with the negative going ramp. The idea here is that whatever the noise we are encountering during negative going ramp will be averaged out in both negative and positive going ramps. So you can see here the slope proportional to EI. This one is the positive going ramp, and here you can see this one is the negative going ramp. T1 is the time period which is indicating the positive going ramp, and T2 we can see we can vary for the negative going ramps. So any variable negative going ramp slopes we can have to be augmented with or combined with the positive going ramps here. These two ramps will help us to average the voltage measurement. These two slopes. Hello? Yeah. So in this way, we are going to make use of both hello. Okay, am I audible there? Okay. So in this way, we are going to use both negative and positive going ramps to average out the noise contained during the voltage measurement. So let us see the circuit operation here. That is very much simple. Figure shows a typical block diagram for the dual slope integration type DVM. Okay, I will repeat it once again. So figure shows a neat block diagram for the typical dual slope integration type DVM. We got here two separate inputs just for explanation conveniency. EI it will indicate positive going RAM. ER it will indicate positive going RAM. ER minus ER it will indicate negative going RAM. So that is controlled with the help of a switch drive that is helping us to switch continuously between positive going RAM and negative going RAM. SI it will be indicating a switch connecting to the EI positive going RAM. SR it will indicate the switch connecting to the minus here that is negative going RAM. So let us start the operation here. We'll start the operation by resetting the counter and displays. You can see here, all of you are observing here. All of you listen this operation carefully. This is very much important. We'll begin the operation by resetting the counter and displays. That is called the calibration. And flip-flop output will be set to 0. Means it is indicating that flip-flop output 0 means we resetted the counter and displays and now we are about to begin the operation of dual slope integration type DVM. So with the state 0 output of flip-flop, we'll tell switch drive to connect switch SI to EI. Switch EI, SI is now connected to EI. Now with the connection connecting to EI, positive going RAM, now we can see only EI we keep in mind, not ER. Okay. With EI connected to the circuit, that is R, with the C, now EI, hello, hello, am I audible? Okay. Now with EI connected, with R and C, it is acting like a integrator. Okay. Now with EI applied here, what current we are getting here? I equal to EI by R. So this much amount of current. What is the amount of current? EI by R amount of current will start flowing through the C, through the capacitor. Now that amount of current will start storing in the capacitor and allowing the capacitor to charge. You can see here in the waveform, during T1 period, your capacitor will slowly go on charging. During T1 period, your capacitor slowly go on charging with the application of EI, with the help of current EI by R. So the slope of this, that indicating the charging of your capacitor, is nothing but directly proportional to the input EI. Okay. Are you getting this point? Okay. Now you can see before the capacitor E0 output of integrator is 0. The moment when you applied EI through R, it will start charging the capacitor. At that moment, its E0 is not going to be equal to 0. So go on increasing. You keep this one in mind. Means what I want to say is that E0 became not equal to 0 the moment when you applied EI. Before that, it was 0. Before, hello? Okay, I will repeat once again. All of you listen carefully. The moment when you applied EI, E0 became non-zero. Before that, E0 is 0. Before that, E0 is 0. Are you getting this point? Okay. Means if we come back to this one, zero detector or a comparator, when E naught is zero, hello? Okay. When E naught is zero, that is continuously the zero detector continuously comparing E naught, that is of integrator, with ground, that is zero. When both are zero, hello? Some network issue, may get a delayed version of my audio. I hope now it may be correct. Okay, where we are? Zero character, zero detector. Hello? Okay. Now this generator or a comparator, what it is doing, it is continuously comparing the output of integrator E naught with the with zero. When both equal, it is exactly XOR gate. When both are zero, its output is zero. Both are equal, its output is zero. When both are not equal, because one of the input is fixed, it is always zero only. But when E naught, the moment E naught not became equal to zero, then output of this zero detector will always be going to high. It will be kept high as long as E naught will never become equal to zero. Again, it should come back to zero, then only its output will become zero. Now, with E naught not equal to zero, with application of EI, with the different two input states, zero detector output will be 1. This one will be applied to this AND gate, and here clock oscillators pulses will always be applied. This is also 1. Then it will start counting the pulses. Now, means with the application of EI, you can see as shown in the waveform, I have indicated here to start counting the pulses. The pulses will be applied the moment when you applied the EI. Means from here. When E naught not became equal to 0, from that instant, the pulses will be applied to the counter. Okay. Now at this point, I have shown start counting, I have indicated here. We will start counting the pulses. Now counter, how long it will count the pulses? What is the maximum reading you are getting? 0, 0, 0 with all digits 9. When all digits will become 9999. I will repeat once again. Now counter will start counting the pulses. Hello? Hello? Okay. Okay, you are with me. It's again a network problem. We are lagging with our audio here. You listen here carefully. Now the counter will be start counting the pulses from 0. How long it will count? The maximum value will be all 4 digits will reach 9999. After that it will be reset back. Okay. So when it will be reset back, flip-flop output which was 0 now change to 1. So initially we started with the 0 flip-flop state with the counter 0. Connected EI, charging capacitor to the peak. From that instant, clock pulses will be applied to the counter. Zero detector output will become 1. Counter will start counting until it will reach 999 or it may be somewhere in the intermediate also, whatever the input we want to measure. So after that it will be reset back, flip-flop output which was 0 to change to 1. Will tell the switch drive to now you can connect from SI to SR with the negative going slope. With the negative going slope connected, will insert this integrator and telling the capacitor to discharge. You can see it is shown in the waveform as a period T2. During period T2, capacitor will start discharging. Once it will reach the 0, E naught will become 0 and 0 detector, when both inputs will become equal to 0, its output will become changed from 1 to 0 once again. When it will output, 0 detector output will become 1 to 0, no more clock pulses will be applied to the counter to be counted, and all those counted pulses will be displayed. That's all. So the operation is very simple. We'll start applying the counting pulses to be counted with application of EI. until we'll get the zero detection during negative slope. During negative slope means the clock pulses will be applied with the application of EI till zero will get during application of minus EM. Okay, means both the slopes will be used here, EI and ER, minus ER. And the noise contained in EI and ER will be eliminated with the help of this integrator. So that's what is known as a dual slope, because we are using both the positive going and negative going slopes. Integration type, that is going to averaging out the noise contained in both the slopes, DVM, like this. So in this way, guys, you need to explain dual slope integration type DVM. So some mathematical part also coming here. During charging, because for the integrator output we know that the output voltage is equal to minus 1 by RC integral from 0 to T1, because it is charging time you can see here T1, and discharging time here you can see it is going to be T2. So during charging, E naught will be given by minus 1 by RC integral from 0 to T1 EI dt. If you integrate that one, we will get it as minus EI T1 by RC. Similarly, during discharging, the time will be T2, that is from 0 to T2. You can resolve it, you will get it as minus ER T2 by RC. So if you compare these two by using these two discharging and charging times, finally we are getting one equation, that is the relationship between the input EI and ER. Or if you replace T2 and T1 in terms of the digital counts N1 and N2, we'll get it as EI equal to N2 by N1 ER. So this is some few formulas we are widely using when you are going to solve the problems related to RAM type and dual slope integration type DVMs. So the advantages or uses of this dual slope type of technique, this has got, you can see the better noise rejection, because superimposed AC are averaged out during the integration process, and because of that we are able to achieve an accuracy up to plus or minus 0.05% in 100 millisecond is available. That is the speed of this dual slope integration type DVM. So these are some numericals which are very simple. Sometimes I have seen, sometimes they have been asked in the VT exam. An integrator contains 100 kilo and 1 microfarad capacitor, that is R and C values of your integrator. If the voltage applied to the integrator input is 1 volt, what voltage will be present at the output of integrator after 1 second? So this is the formula just now we have discussed in the previous slide. You remember that one? We are using that one in the solving the problem like this. E naught equal to EI T1 by RC. T1 is given in the problem, that is a 1 second. R and C has been given, the R and C values of integrator. We will get the output voltage 10 volt, integrated output voltage 10 volt. Similar problem. Now if a reference voltage is applied to the integrator of the above example, that is a continuation of that only at time T1 is 5 volt in amplitude, then how you can get the charging period T2? This is the another version of the same formula, that is EI T1 by RC equal to ER T2 by RC. So you can substitute the things here. EI T1 and RC is given. ER just now you got 10 volt, that is RC is given. You can just find out T2. So problems are very simple and it's direct substitution. Only thing you need to remember the formulas. So another few formulas which are quite quite different here. An integrator has 100K and 2 microfarad capacitor. If the applied voltage is 2 volt, what will be the output of integrator after 2 seconds? You can use this formula. Input voltage is a EI, that is a 2 volt. Time is given, that is a 2 second. RC values are given. You can substitute, will get the output voltage. Same is similar to the previous two problems. So guys, today we have discussed important points like how to define DVM, what parameters to be kept in mind when you're going to design or choose digital voltmeters. Then we have seen some important features or performance features of your digital voltmeter. And we came across two important types of DVMs, RAM type DVM, how to explain it with the help of block diagram and neat waveform, and what drawback it has got, and how it can be overcome with the help of dual slope integration type DVM with the help of a neat block diagram and waveforms. And also we have gone through its mathematical derivations and some numericals also we have seen.